So in this video, we can look at momentum and conservation of momentum in collisions. And this video is divided into chapters, so you can skip to the chapter you want. So first chapter, we can look at what momentum is and how to calculate it. In the second chapter, there's a short exercise and practice in using the equations, and I'll then go through the answers. Chapter 3 is explaining conservation of momentum in collisions. Chapter 4 will be giving you an example of a question on conservation of momentum in collisions. And finally, Chapter 5 will give you the opportunity to apply conservation of momentum to collisions in questions, and then I'll work through the answers afterwards. There are two other videos that follow on from this. The first one is conservation of momentum in explosions and applying Newton's third law. And the second one is exam question practice with worked answers on both collisions and explosions. So first of all, momentum is a quality of a moving object. But what is it? Well, let's have a look. Which will be hardest to stop? A racing car on a track or a car in a city? Well, of course, it's going to be the racing car on the track because it's got a much higher speed, so it's got more kinetic energy. So momentum is about really thinking about the stoppability of an object as well. So it's going to be harder to stop the racing car. But now let's have a look at these ones. Which is going to be harder to stop? Of course, a car travelling in the city or a bus travelling in the city. Of course, it's going to be the bus because it's got a lot more mass. The quality of a moving object, and it depends on both the mass and the speed of the object. So momentum is mass times the velocity. And because mass must be in kilograms, velocity is in meters per second, that makes the unit of momentum kilogram meter per second. In your exam paper and in your equation sheet, you will see momentum also written as P, standing for momentum, is mass times velocity, and that's the equation that I'm going to be writing because it's much quicker. If you need to put it in a triangle to rearrange, it goes like that, and of course therefore mass is momentum over velocity, and velocity is momentum over mass. And finally, momentum is a vector quantity, so it has size and direction. Let me give you an example. If you've got a car of mass 2,000 kilograms travelling that way, let's make that velocity positive because velocity is a vector, then the momentum is mass times velocity, which is 40,000, and it's plus because it's going that way. If the car was going the opposite direction, its velocity is negative. So it's travelling at minus 20 meters a second. That just tells you it's travelling the opposite direction, which means the momentum, if you multiply the two together, is minus 40,000 kilogram meters a second. That just tells you that it's travelling in the opposite direction. So momentum is a vector. So what I want you to do now is to pause the video and have a go at applying that equation to these questions. So we have momentum is mass times velocity, which is equal to 80,000 times by 300, and that gave you 24 million kilogram meters per second. If you press your Eng button, you will find that that converts it straight to engineering form, which is really, really useful, rather than you having to write out all those numbers. The second one, again, quote the equation first, and this time be really careful because your mass is in grams, so divide by 1,000 is 0.5, times by your speed will give you 5 kilogram meters per second. And finally, the last one again, I've given you in grams, you need to divide by 1,000. So momentum is mass times velocity, which is 0.06 kilograms times 3, which is 0.18 kilogram meters per second. So now have a go at these three questions. They give you the momentum and the speed, and I want you to work out the mass for the first one, and for the second one I want you to work out the velocity, and this one is slightly more challenging. Pause the video and off you go. I'd always quote the original equation first, then we need to arrange for mass, which is momentum over velocity, so that's 520 divided by 8, which gives you 65 kilograms. The second one, you will need to put times 10 to the 8 in, and so just remember to press that button for times 10 to the 8, not your times button, and that will bring up this symbol straight away, and you can just put the 8 on. So we've got to work out the velocity. So again, quote the original equation. Then so velocity is momentum divided by mass, and that gives you 6 times 10 to the 8 divided by 3 times 10 to the 8, which is equal to 200 meters per second. Finally, the last question tells you the cyclist is 60 kilograms, but it tells you the initial velocity is 15 meters a second, but then the cyclist obviously speeds up and gains that much momentum afterwards. So what's the final speed? The first thing we need to do is to work out the increase in speed, which is related to this increase in momentum. So we've got momentum is mass times velocity. So the increase in velocity will be momentum divided by mass, which is going to be 600 divided by 60, which equals 10 meters per second. So that's the increase in speed. So the final speed will be your initial speed plus your increase in speed, which should give you 25 meters per second. So what we're now going to do is look at what happens to momentum in collisions. And I haven't got time to go through all the practicals with you, but I'm going to show you one practical and then we'll look at some of the data to see what happens. So what video you're going to see in a minute is this frictionless track. Now it's nearly frictionless, which means that there are no external forces acting. The only forces acting are when this cart hits this cart. And I'm going to push this cart quite fast going this way. This cart weighs exactly 1 kilogram, it's engineered to. And when it moves through this light gate, because it's going to cut the infrared beam here, this light gate will measure the speed at which it goes to that light gate. And then we can work out its momentum. Once it's gone through the light gate, this bit's gone through the light gate, make sure it all goes through first, it's going to stick with Velcro to this cart here, which also weighs 1 kilogram. That will slow the two down. So that's the collision. And once it's hit this and slowed down, this interrupt card will go through this light gate and it will measure the speed after the collision. So that will measure the speed before, that will measure the speed after. And you can see that there. So let's have a quick look at the video. It is very fast, but it will bring you up the velocities before and after, and then we'll do some analysis. So the velocity before was 0.479, and then afterwards we had double the mass stuck together, 2 kilograms, and you can see the velocity has roughly halved. So let's look at calculating the momentum. The momentum before is just mass times velocity, so that's 1 times that, which is 0.479. The momentum afterwards will be the total mass of both of them, which is 2 times their new speed, 0.236. And can you see that is nearly the same? So it looks like momentum is conserved, and momentum before is equal to momentum afterwards. I then did this for 2 more experiments. So what we did this time is you can add exact kilogram mass to the top and screw it in. to the second trolley. So now we've got a mass afterwards of exactly 3 kilograms. And that was the velocity before. I obviously pushed it a bit harder. And afterwards, the total mass is 3. Notice that that has dropped about 3 times. And if we find out what the momentums before are, and 3 times 0.171, the momentum afterwards, you can see as well in experimental error, those two momentums are roughly the same. And finally, I added another kilogram to the second cart. So we've got a total mass of 3 kilograms on this one. And these were the results there. Obviously pushed it slightly slower, this cart here. That's the momentum before. You'll notice that this time the speed has dropped by roughly 4 times because we've got 4 times the mass after compared to before, and multiply the two together, you can see the momentum is roughly the same. So in collisions, the momentum after the collision is the same as the momentum before a collision, as long as no other external forces act. So if there was a massive amount of friction on the surface here, then before it got to the light gate, it would slow down and we wouldn't get the right result. So it's called a closed system because no other forces act except the forces between one trolley and the other. So this is conservation of momentum. In a closed system, which means no external forces act, the total momentum before a collision equals the total momentum after a collision. So let's see how we can apply that to a question on collisions. So in this example, it says a trolley of mass 0.5 kilograms travelling at a velocity of 1.2 meters per second collides with a stationary trolley of 1.5 kilograms, which is stationary. I'd love to do this in a supermarket car park. Imagine they both slot in together, so they're stuck together, and all your exam questions will be having the objects stuck together after the collision. You have to go into A level where they don't stick together. So afterwards, they have a total combined mass of 2 kilograms. And the question is, what's the velocity of the trolleys after the collision when they stuck together? So first of all, we're going to work out the momentum before the collision. And of course, that's equal to P, which is mass times velocity. And so the mass is 0.5, the velocity is 1.2. That's for the first trolley. This trolley doesn't have any momentum, it's not moving. So the total momentum of that trolley is 0.6 kilogram meters per second. Now we've got to remember as well that the momentum afterwards is the same as the momentum before. So we know the momentum of these trolleys afterwards, we know the mass, so we need to just find the velocity. So the momentum after is going to equal 0.6, which is going to equal the new mass 2 times the velocity we don't know. And all we need to do is rearrange that equation by taking 2 down to the side. So velocity is 0.6 divided by 2, which is 0.3 meters per second. What I'd like you to do now is to pause the video and have a go at these questions. If you get stuck on one of them, just go forward to my worked answers on the next chapter and then come back. So in the first question, you first worked out the momentum before, which is just the mass times velocity, which gave you 20,000. You then wrote down the momentum afterwards is the same 20,000, which is going to be the new mass, which is 2,000 because they've stuck together, times the velocity. So therefore the velocity is 20,000 divided by 2,000. So that's 10. I've this time used velocity rather than V just to help students, but you can just use V for that. The second one, momentum before, is mass times velocity. So again, that's 2,000 times 5, which is 10,000, kilogram meters a second. So the momentum after is going to be the same, 10,000, which is going to equal the new mass, because they're both stuck together, the car and the bike, which is 2,500 times velocity. So therefore velocity is 10,000 divided by 2,500, which gives you 4. Question 3, the momentum before again is just mass times velocity, which is 24,000. So momentum afterwards, conservation momentum, will also be 24,000, which is going to be the new mass. So add those two together, will give you 13,500 times your velocity. So velocity is 24,000 divided by 13,500, which gives you 1.8. And finally, the last question, momentum is mass times velocity again. So that's 2,500 times 12 is 30,000. Momentum afterwards must be the same for conservation momentum. So that's going to equal the new mass of both of them stuck together, 3,200 times the velocity. So finally, velocity is 3,000 divided by 3,200, which does give you 9.4. So if you've got all those, well done, because those are the hardest questions you'd get in terms of those calculations for collisions. And finally, don't forget, there are 2 more videos. One is on conservation momentum in explosions rather than collisions, and then applying Newton's third law to explain what happens in explosions. And then the final video is how do you link this to exam questions.